Okay, good afternoon, everybody. Okay, so today we are going to practice with Copasi. If you don't have your laptop here, I will be recording what we go through. We'll go through some screen recording and stuff of how to sort of set up and use it. So if you prefer to sort of just watch and learn and then try it after, go for it. If you'd like to do it live, that's helpful. Again, I want to make sure we go through part of the content. So even if you are practicing and struggling it, I may go faster than you prefer, because the goal of this one is to give you a visual example, and then I want you guys to practice with this, okay? So where we left off, we introduced catalytic steady states. So this is where we say the most basic catalytic mechanism derives from the Michaelis-Menten system. When we say Michaelis-Menten, all we're saying is I have one catalyst which has one substrate being turned to one product. That simplifies it because there's a single intermediate, what we call the enzyme substrate complex, and then a irreversible, or the slow step, usually is set up as the second step. This is just a generality of a lot of biochemical systems, is a rapid pre-equilibrium followed by your catalytically responsible step to sort of dissociate that. Again, remember, all reactions are in principle reversible, but one thing you'll start to see, especially when you start dealing with catalytic systems, the step that becomes the rate limiting or turnover limiting step is usually set as your irreversible step, just by default. All we're really saying is that while this potentially could go backwards, the reason that substrate turns to product is there's effectively like a ratchet. There has to be one step that goes one way predominantly, and then as a result of that, the reverse reaction, the K minus cat, happens to be small enough it's negligible, and we end up setting the system up with a pre-equilibrium followed by a single unidirectional reaction. We went through the point of this point saying, okay, we got a fast and slow step. Steady state approximation describing the enzyme substrate complex gives you this equation where D intermediate dt is set to 0. And again, 3 elementary steps based on the 3 Ks that we've been provided. If we go through this, we have 2 unknowns, what we call free enzyme, that kind of green E, and then the enzyme substrate complex, the bound enzyme, so catalyst and free catalyst. Or free catalyst and our first intermediate that involves the catalyst. We have to have the mass balance equation. We go through the same algebra we did before, and we end up with our sort of 1+ form. This is a generic form for any steady state rate equation. Again, what we say here is when we do this approximation, this is the mathematically true equation for any single substrate, single product, 3 different elementary steps. What happens is you get case-specific modifications. So one we showed you through that usually when you've seen in the biology world, the Michaelis-Menten equation is usually it makes it look more simple, because what we're doing is binning together Kcat and total, what they call Vmax, and then Km is just an aggregation of the rate terms, the individual rate constants more as an equilibrium constant. But what we have here is when you're evaluating a catalyst, the system can behave very differently with respect to substrate, no matter what those K values are. So we end up with 2 different simplifications. So the overall general equation looks like that. If the substrate concentration is very, very large, especially relative to your K values, basically this denominator is dominated by your substrate, Km disappears, this becomes Kcat, substrate, E total over only substrate, which means we can cancel that out. And then it just drops to Vmax, Kcat times total. It's just a constant of your total enzyme concentration and your Kcat concentration. So effectively, if the substrate concentration is very large, especially relative to these Km values, then it simplifies to just a 0-order process. Adding more substrate does not make it go faster because we've saturated the system. We can't push it any quicker because the enzyme's doing its best. That's a fundamental of a particular enzyme. The same system, though, depending on what happens, is if we have very low substrate concentration, so this is near the end of a reaction or a case where you have a ton of enzymes and very little substrate, the same equation will simplify the other way, where that is tiny, Km is large, the denominator is really just Vmax substrate Km, or Kcat E total substrate over Km, so you end up with the entire equation. Basically, we just lose that plus S term in the denominator. So what you have is a region of the catalysis that will look first order in substrate under these cases, and a region of the catalytic system that will look 0 order in substrate. And this comes back to this kind of conversation of order we started the last week. Order is subjective. Like when we say a reaction is first order, we're making that assumption within a certain finite region of substrate concentration. So this goes back to, I'll go through this one in just a second. So under those two different sort of divergences, what we can do is plot, this is the normal Michaelis-Menten sort of plot, where we're plotting the rate of the reaction on the y and the substrate concentration on the s. Now normally how you would do this is a bunch of initial rate equations. What you do is take a certain enzyme concentration, hold that fixed. You would start the reaction where you throw in a certain amount of substrate, and let's say that's this data point down here. I would pick a certain initial concentration of substrate, I would run the reaction, I would measure the initial rate of that reaction, that gives me a single data point. Then I increase the substrate concentration and I see a change in rate. And I keep doing that, dot, 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 all the way up, and I build up this curve through a whole bunch of initial rate measurements. And again, we do this as initial rate measurements because we're assuming that as the reaction runs, maybe the enzyme's dying, maybe the product is inhibiting, something goes wrong, so we're taking that initial snapshot of rate, and this curve is made up through potentially sometimes hundreds of experiments. Has anybody had to do this for enzymes? Did you have to do it for biology, like for a biochem experiment? Yeah? And how did you end up so is this a daily thing for you to do in your research program, or is it just sort of an undergrad thing that you had to do at one point?
It was undergrad in a project.
If you remember probably how this went, what you're looking for, and the reason that we do this is because in Michaelis-Menten, they actually went through and systematized the Km values, which were sort of like for different substrates. We usually call Km the binding constant. Like 1/Km talks about how tightly a substrate binds to a certain enzyme. So that means if I've got a whole bunch of different lipases, I can actually rank them by saying the Km of these different systems has certain values. It talks about how tightly they like certain substrates, and you can use it as like a colligative property. Vmax is talking about how fast that enzyme will turn over under any system. So these two values were sort of like barcodes for different enzymes. You could tell if those enzymes came from different species because of differences in Km and Vmax for those particular ones. You knew that there's a genetic manipulation somewhere because the performance was different. So solving these was hard. Usually what that meant is many, many experiments, because you've got to find this value. You don't know where it is. So you're usually doing multiple experiments as you're increasing substrate. This becomes impractical because in certain cases, you may not be reaching this asymptotic value. The substrate starts precipitating in the system that's equivalent to your enzyme. Like up here, these are sometimes very weird systems that are nowhere close to how the enzyme's used to running. So solving this empirically usually means get a bunch of values, assume this equation fits, and actually put it into some type of a nonlinear fitting software and solve for Km and Vmax based on the shape of the curve. You're just assuming that this will be true for all concentrations and you can extrapolate it. But this, what I'm trying to emphasize is it's inappropriate to say a catalytic reaction is first order in a substrate. That is only true given certain context. It is first order in this concentration of substrate, but if you're always operating over here, it'll look like it's under saturation kinetics. It'll look zero order effectively. So order is not a holy value. One thing I want to go back to this point, did everybody take a quick look at this Python code of basically going through and doing this is how you do algebra with Python. Did anybody have a quick shot at this? Anybody try to actually implement it? Yeah? How did it go? Give me feedback. Was it super easy? Were you totally confused? Did you not get out of the gate? I need feedback to understand how much I need to fill in.
I thought it was good, but I don't know if I'm the best person
To judge, okay.
to judge. Yeah.
Again, feedback. What do you guys think? How are you able to start a Python environment and plug in this code? Who can do that? Yeah? Who can definitely not even do that? All right, so I'll put up a review of how to even get started on this kind of part. As a first, I want you guys to try it. Again, visually, I'll give you a quick part. What we're doing in this code, up here, this is where you're bringing in libraries, the SymPy library. What you're doing is that's a whole set of functions that lets you do math. That's all that is. So you're bringing this part in. Over here, what you're saying is, I have these things, text values, that I am going to call variables. You can put anything you want. You can call this Bob, Steve, whatever, but these are just labels that allow me to sort of talk about what math I'm going to do. This is where I'm defining. There's something I'm calling x, y, in this case int, which I'm calling my intermediate, placeholder, kcat, these are just values that when I'm doing my algebra down here, I have to label what those values are. You are free to call them whatever you want. This is just a standard I'm trying to go through. The one thing I do want to mention, subscript does not show up in Python. Like when you're doing this, it's just single lines. You can't call it k sub 1 or k sub 2. This is just a single line, no text. Second thing too is you can't have k minus 2. This is just a problem of how Python understands what you're saying. If you drew k minus 2, it thinks you're doing math. It thinks you're saying k minus the numerical value 2. So what we have to do just by here, I have to call everything as k1, k2, kcat. I got to give it a script basically. So where typically you would normally call it k1, k minus 1, it just means you need to map these variables onto your ChemDraw where you're just specifically calling these specific values. This is why when usually you're doing this in a practice, I'll walk you guys through. As you're building out your rate equations and as you're doing your modeling, a really good practice to do is you draw your ChemDraw, get all your labels set up in ChemDraw, then you work on your modeling software. So this is your guide of what you called things, and that way you don't get lost as you're going back and forth between the two. Down here, these are just your equations. I'm saying these variables, so catalyst total is what I'm calling CT, the free catalyst, catalyst total, and an intermediate. That's my mass balance equation. The steady state equation is just these variables. That's my 3 different rate constants I've described. So my forward, my back, and my kcat. And then the actual overall rate law, that's the final equation in my Michaelis-Menten system. Then all I'm doing down here, this is the math. I'm saying my rate law, the final thing, is equal to this, where I'm subbing in and going through and solving for the 2 values, the steady state value and the intermediate value based on these 2 equations up here. And then at the end, it'll plot my rate law value at the end of it. Again, if this is something that's very unfamiliar, it's a good practice. You need to get this far. What I would, again, I will plot, or I'll put up a quick video on how you should be able to do this step by step. Another thing I'd encourage you though is take this, go to ChatGPT, and have it walk you through getting this implemented and running on your computer. If you've never done something like this is really, really useful because you can take this code, copy and paste it, throw it into ChatGPT and say, this is what I'm trying to do. Help me to open a Python environment on my computer. And you can even specify, I want to use a Jupyter notebook for doing this, and it'll walk you through how to do this. That practice is something that you should get familiar with because what it'll go through is it'll help you to sort of fill in that gap. It's your expert friend you can sort of tap and go through this. Something as simple as this, you should have no problem getting a language model to walk you through this. ChatGPT, Claude, Gemini, whatever you want, all of them have some capacity to this. What I do have is a link down here, which is the Google Colab space. I think this is still active. This is hosted by the HeinLab space. What you should be able to do is link into this. It will share to you. You should be able to basically load this Jupyter notebook and just use it, and just basically run it because it's being hosted in an environment online. This is just the description of what those values are. So the 3 equations here, my catalyst total is just the mass balance equation. That's my steady state approximation. And this is the rate law, which is my d product dt, which in the end, the notebook output should give you this, which looks like what you have over here. The only difference if you map between these two is what we've called things. Formalization before, we called k1 and k minus 1. That's now represented as k1 and k2, where I'm just basically calling, again, like I said, there's that problem that sub minus 1 is not something I can represent in the text. So the only difference between what you see here and what you see here is just it's nomenclature. You should be able to map this equation against this output based on what we've sort of drawn in terms of our symbol diagrams. Okay, that's that. Now we're going to go more complex. So before the Michaelis-Menten equation I gave you is 1 substrate, 1 enzyme. Who runs those reactions in organic chemistry? Better be freaking nobody, right? Like we do not take a single substrate and a single catalyst. This is way more common. You are taking 2 things and 1 enzyme and 1 catalyst to do something. This is the template, what we call a triangle, because you have 3 points here. Free catalyst, I have my first intermediate, a binding. I have a second intermediate where I'm now bringing 2 pieces together, and then I have a product forming step. This is the archetypical palladium catalyzed cross-coupling reaction. Almost any single catalytic system, if it's a proline catalyzed reaction, anything that's a simple point where catalyst binds something, binds a second thing, and then spits out product will map over this kind of an equation. So this is something that's really useful because it can be reused in almost any catalytic system you're dealing with, whether it's light, whether it's proton catalyzed. This works. And this is the real challenge, is being able to take really complicated systems and map them over this generic cycle. Because what you'll find is no matter how complex something is, kinetically, a catalyst binding a certain component where there's two concentrations that can deal with to make one intermediate, that intermediate interacting with some other reagent to give me a second intermediate, and then on to product, will eventually be something you can reduce any catalytic system to. But it's about finding that generic sort of map. The problem with this one, when you actually get into the math, is it gets hella more complicated. So this will be your first thing I want you guys to do, is by some means, that's the rate equation for this. And you can see what I've done here is I've actually had at another step over here where my free catalyst, my substrate, or the catalyst I'd add to this undergoes a catalyst activation step. This could be something like adding palladium acetate plus ligand to make the real catalyst that sits on cycle, and then I have my overall equation where I have a reversible oxidation, this first binding. This second one is irreversible. This third step is irreversible. This activation is irreversible. So if you took this, you should be able to walk through, using the things I showed you these last couple lectures, you should be able to set up each equation, and you should be able to solve for this. I think actually, looking at this one, I think actually I'm not using that step in this equation. You can check that here, K1, K3 right there, and K4. This step here, I have no K value associated with it, so I'm actually not solving for that first step in this equation. This one's just assuming you have only 3 different parts of this equilibrium: free catalyst, first intermediate, second intermediate. But that's what you should be able to derive. And only this is what keeps happening. It's algebra. No matter how many complicated intermediates you have, this equation will get more and more complex as you start to add things to the system. That's why having tools like Maple, like the Python solver, is very useful, because then you don't have to rely on your own algebra to go through and make mistakes, right? But you should have some visual complexity. The other thing I wanted to emphasize, though, is that even though this is up here at the top, this is mathematically the true steady state equation for any 3-part catalytic system where you have one thing going in, a reversible first step, irreversible second step, irreversible product formation. That is the true full equation you will get for it. It gets more complex if I have reversible steps here and here. I just get more K values and more other constants that will sort of expand. But any single catalytic system with this form will reduce to that general equation. Now what happens practically is the same thing we saw for Michaelis-Menten. This is the general case. But if transmetallation is limiting, so that K3 here is our limiting step, what we're really saying is what happens to K3? It's going to be very, very, very small relative to the other ones, which means I can take this general equation and start that process of going through and doing simplification. So if K3 is tiny compared to anything else, this term right here, AB, K1, K3, that dies, right? It's gone. And this term, K3, K4b, because it's a multiplicative of, think of it like 0. If you set K3 equal to 0, AB, K1, K3 dies, K3, K4b dies, you get this guy, right? So I've just dropped out 2 terms from my denominator. Okay, that's more simple. To go from here to here, now what you're doing is you're just saying, look, I have a common term of K4 in my denominator. If I factor that out, it disappears from the top and the bottom. So K4 no longer matters. What we're saying there is the reductive elimination is not really in part for the driving this reaction. The rate isn't responded to this split because the slow step is right here at K3. So K4 drops out. Cool. Now we're down to here. Okay, how do I go from here to here? What's the assumption that has to go from that to that? If you look at this second one here where we have K2, K1a, and we're just getting down to K1a. K2 is very small. If you look at where K2 is, that's right here, right? That's the reverse reaction for that first step. What are we saying with that assumption? If I'm saying K2 is small relative to K1, what am I really saying?
You can think about it as irreversible.
It's getting close to irreversible. You're setting K2 close to 0. Yeah, there's something else, another way you could describe that. This right here is what? Forward and backwards. This is a reversible equilibrium, right? If I set K2 small, and especially much smaller than K1, is this a product facing equilibrium or starting material facing equilibrium? product facing. I'm saying that when I take my palladium in this species, yes, it's in equilibrium, but it's really product facing. It's like a really, the oxidative addition towards that intermediate is very highly favored. So yeah, you're basically saying that K2 is negligible, especially relative to K1. It's a highly product facing equilibrium. Now, so that's the second assumption I have to make, but by doing that, K2 disappears. I now have this guy. Now K1 cancels, A cancels. Now I'm down to this, right? Boop, boop, and then that step over here, I didn't, well, that's wrong, right? A should be gone, and K1 should be gone, right? So amnesia dust, you don't see this. That's got to be gone. The denominator is dead, right? This is just K3, B, cat total. No denominator there. So now what we're saying is, given those two assumptions, here's the complex system. Assumption number one, K3 is much smaller than any other step. That's my turnover limiting step. Second assumption, the first equilibrium is very product favored. So K2 is very small compared to K1. Given those two, this becomes a very simple first order equation. It's just d product dt is now equal to K3, this transmetallation step, concentration of B, that's the thing that's involving in that step, that's the whatever this reagent is. If this was a Suzuki reaction, that'd be my boronic acid, right, the transmetallation. And then the concentration of the catalyst, how much stuff I have on cycle here. The denominator disappears in the bottom in that point. So it's now just a very simple first order reaction. Again, that's not true always. What would happen to this system if B was, like look back to the generic equation now. You always want to think of this system, that generic equation is secretly hiding behind this catalytic system. Depending on the absolute values of K1, B, your concentrations, A, B, and cat, and depending on the size of your Ks, it will simplify in a couple different ways depending on what these ratios are. At some point in time, even if this was true, the simplification was true, what would happen to the system if B was really, really, really small and A was really big? For like actually both of them, let's say both are small. If B gets really small and A gets really small, what might happen to this system? Yeah?
You would end up with just K2 and K4 in the denominator, which would then lead you to a numerator that is effectively all that divided by K2.
So you're looking at which one are you simplifying up here? So you're saying A and B are really tiny.
Yeah.
So all the concentrations disappear. Yeah.
So your denominator becomes just K2 and K4.
Right. So what does the numerator look like then?
It depends if you assume that negligible in the numerator as well.
You never do that, right? When we say negligible, we're doing simplifications to the denominator. We're saying that those are basically some values are more important than others. So this denominator becomes, effectively zero, not zero. The reason we do that simplification down here is it simplifies it. Numerator is both A, B, and cat now. All we're saying is that the reaction reaches the very end, those final turnovers, the concentrations of A and B suddenly matter a lot because it almost becomes a second order process then. That's why that if you have a system like this, it'll take off and follow first order kinetics beautifully. And as you get to those last turnovers, it's trying to find those last couple molecules of A to get this first step into happen, and it's going to slow down until it can find this. So it suddenly has an order dependence in A as those fast turnovers come in. And same thing, you can actually take this equilibrium and reverse it. If this step here was actually a very starting material facing equilibrium, this would be first order in A, not first order in B again. So you can do any manipulation of the system to actually look at those different parts. How does that feel from this makes sense, you think you can manipulate and use this? We're going to practice a couple systems on it, but the thing I want you to really internalize, that equation, it rules most of the catalytic systems that you're seeing. And what happens is applying it comes down to the absolute concentrations of A, B, and cat and the K values. It's super important because most of your systems can actually apply directly to this. The only thing that gets more complex is if we wanted to make these reversible instead of irreversible, if we start adding catalyst activation, if we start adding intermediate decomposition, you start adding more constants, you can increase the complexity. But think of this as the base case that you'll probably run into with most of your systems. Okay. So this is just the step-by-step of how you go through this. I'm going to assign this to you guys as something I want you guys to try longhand to do this actual simplification. I've included the Python that you would need. It gets more complicated because we have two things to simplify now. So these Python applications and the Colab is actually, the Google Colab link is actually in place. This allows you to go through and actually do the solving or solution finding for this one too. If you go through it, it'll give you your final rate equation that looks like this, which again, the naming of it, naming convention based on what we called K1 and K minus 1 is different, but they have the same form between the two. Okay, that's the algebra part. If you hate algebra, this is where we use Copasi. So Copasi is a wonderful way to do what I'd consider visual kinetics. It's a modeling software that lets you set up these equations and try these hypotheses live. The main thing I want you to get from this is when you have these questions like, but wait a minute, what might happen if K1 was small or K3 is small? After you set up the equation in here, you can actually run it, create curves, and answer that question for yourself by doing like a digital experiment of what a reaction would look like. So this is how you do this. When you first open Copasi, you should get something like this. You've got a couple of different tabs over here. I'm showing you how to use this particular GUI, and there's other tutorials online that actually do this fully in Python. Up to you of how you'd like to use it, but I'll show you what I would use for using the GUI that's available. First thing you do is you go to the Model tab. So there's 4 tabs: Model, Tasks, Outputs, and Functions. You're really going to use Models, Tasks, which is made up of what you want to run. Mainly we're going to do the time course experiments initially. Outputs is basically what do you see. These are the plots that you have to create and the visualization that you're going to do. So we're going to start up here under Biochemical. You use these little hashes to drop down menus. So I'm going to drop down Biochemical, and you can see it opens up. We've got compartments, species, reactions. Those are the most important ones, and global quantities. What these really correspond to is reactions. These are the elementary steps of the model that you are going to fill in. So this is where if I have 4 or 5 steps in my ChemDraw, this is where I need to populate those individual reactions. Species, this is everything. Anything that has a concentration, including an intermediate, substrate, a product, will show up in here. The global quantities, this is where we've got things like rate constants, initial concentrations. So we'll go back to that. So I start usually here in the Reactions tab. You go up and click on New Reaction, so I just double click. It opens up this notation. This is something that for hygiene, you need to kind of come up, it's a lot like coding, where you need to kind of follow a certain subscriptive practice, where the syntax and your habits should be practice having good sort of notation. When it starts, it'll always call it reaction. I usually will rename this first. I'm going to call it reaction number 1, RxN1. So what we're going to be building in here is this, right? So I'm going to use this as a template for what I need. I'm going to say reaction 1 is this first step right here. So it's the palladium 0 to intermediate, and I have a reversible step that's binding my aryl halide. That's what I'm going to set up. So in this reaction, the way the syntax goes is I am binding. So look at this. If I had to just look at this step here, how would I write what species do I need on the left side of my equilibrium arrow and the right side of the equilibrium arrow for just this set here, forward and back? So what turns to what, basically? Yeah.
The palladium 0 complex plus aryl halide.
Yep.
Becomes the palladium 2 complex.
Yeah, that plus that's got to give this. And we want it to be in equilibrium. You could set this up individually, but what I'm really saying is palladium. You can call it palladium. I'm going to call it, we'll call it palladium. So PD. As your notation, PD is different than capital PD. So pick something, stick with it, right? Because it doesn't understand the difference between your capitalization. So I'm going to call palladium lowercase pd as a material, plus aryl halide. So I'm going to call that capital ARX, right? The notation for equilibrium is just the equal sign. So if I say like palladium plus aryl halide equals, I'm saying it's a reversible equilibrium, is going to equal to my intermediate 1, right? Whatever that species is. When I click enter, what you'll see is it should populate this out. I now have 2 values, a forward and a backward equilibrium constant. The forward one is going to associate palladium and aryl halide. The reverse is just intermediate, so that's basically talking about these 2 species and 2 K values. you notice it should auto-populate into mass action reversible. Depending on how you set it up, it may, these are defaults in your system, it may just choose to use constant flux. Mass action reversible is the more common one you guys are used to. That's basically saying I have two equilibriums, forward and back. Depending on the concentration of both, I can drive it to one side or the other. So just as a standard, check this. Sometimes it will, depending on the settings of your system, it may decide that, oh no, we're going to use constant flux. Very similar, it should behave similar. Some of your fitting values will be different after that. That's first step, and when we're done, I commit it, and what you look happens here is under reaction, I now have one reaction. If I go under species, I now have three species, aryl halide, intermediate, and palladium. Okay, so I've got one experiment. If I go back, I want a new reaction. This is reaction 2, RxN2. Now back to our diagram. That's this one right here. So what do I need to draw that one out? Using the nomenclature I provided, what should that look like?
So you'll need intermediate 1
Yeah,
plus your MR.
yeah,
Will lead to your MX, and then we can say intermediate 2.
yep. So two intermediate, I'm taking that plus this. It is now irreversible. I'm going to say it goes one way only because I only have a single K I'm considering. And that's going to give me these two things, right? So I'm going to draw this out as, remember, this is where having your species open is good. I called int1, lowercase. So I start with that, int1. I'm going to call it whatever, mr, whatever you want to call this guy here, metal r, sure. Irreversible looks like dash arrow. So you use the, what's that, greater than or less than? Greater than. It's all you're doing is using hyphen that to make a little arrow looking caret. So it's hyphen greater than space. And my two products in this case, I'm going to call it intermediate 2 and MX, right? The salt form of this product in this case. Okay, once again, I commit that. And if you look at that, I have one reaction, one K value, 2 steps. I have nothing, like the reverse reaction, intermediate 2 MX does not show up here because it is in that form. If I erase this and said equals and then commit that, you'll see it pops up now where I have forward and backwards, right? So you can actually do this where they're both, you can make it more complicated, but we're going to consider it according to that, which gives you only that 2. You notice up here, I have intermediate 1, I've now added intermediate 2, I also defined MR, my metal complex, the R and this MX. So those are now shown up. If you ever do something like this, where I have capital intermediate and I commit it, you'll see what will happen is intermediate 1, intermediate 2, lowercase, I've got this weird one here, big. You can actually go through and click through, and I say, look, if I click on this one, int1, it says capital I int1 is involved in reaction 2. Lowercase I int1 is involved in reaction 1. That's not what I wanted, right? Well, effectively what I've done is I've got one chemistry that's forming intermediate 1 and this other special thing that is now capital I int1 being reacted 2. They're not connected to each other. So what I want to do is go back to number 2. I'm going to change this back to lowercase, commit. And now if you look at intermediate 1 lowercase, it's involved where it is formed, product of first step, and used in the second step. That's the normal sequence that I'm looking for. And if I go back and click on my uppercase intermediate, it's not involved in any step. So I can actually go through and just delete that species. It's not part of my system. Okay, so I've got 2 reactions now. That's reaction 2. Once again, I need the last one. So I need to get from here to here now to regenerate. So what does that look like? RxN3. How would I write that equation? Somebody give me a suggestion.
Int2 goes to product plus PD.
Yeah, that's the really key thing. So it's, again, I'm using this, it's int2, irreversibly goes to product, PDT. If you just stop here, this is the most common things people do wrong when they build catalytic systems. You go through and you're like, yeah, int2 goes to product, and you don't regenerate your catalyst. It's not a catalytic system. You're not going to get around any other cycle because you're using palladium stoichiometrically. Remember, Copasi is a modeling software. It is nothing. It does not understand chemistry. You can say any crazy reaction, any 4 or 5 component reaction you think is possible, you can define. I could write this and say For example, I could actually write one step that says palladium plus A plus intermediate plus this plus this plus this all becomes product in one big sentence. And it'll go, sure, I'll try to model that. So you have to be the one that's kind of looking over this. And that's why having your chem draw and your thing open where you're doing that sort of line by line annotation is very, very helpful. And yeah, always remember, you need to close the loop where this is forming your catalyst. In this case, I called catalyst PD. That's my free catalyst, and I commit it. You can go through now and look at the species and follow through. So I start the reaction with aryl halide. It's involved in the first step where my palladium plus aryl halide makes int1. I click on int1. int1 is formed there and used up here. That looks good, making int2. Okay, click on int2. int2 is formed here and used up here. And then I get back to my free catalyst. Palladium is at the first step and the third step. So it's used up in the first and formed in the last. This is fine. I have made a complete cycle, right? After you've done this, file, save this. Palladium. I don't know about you guys, but it crashes constantly.
Definitely does.
Depends on which computer you have. But I'll save this one. I'll upload these Copacity files for you guys to play with. So anything we do in class, you'll have them to use the same files that we did. Okay, that's step one. And again, depending on how crazy you want to get, you can build any reaction network that's as complicated as you want. It's just good hygiene about how you code this thing out is a really important part. Now that this is done, what we want to do is go to the global quantities tab. Sorry, not global quantities. I want to go to parameter overview. So this is a sum of everything that's going on in the system. You can see that in the end, I've got initial time is equal to 0. I've got one compartment. That means I have a homogeneous reaction with just one thing in phase. I don't have a bilayer. I don't have two different liquids. You can get really complicated where you have mass balance transfer, where you've got, because this was originally built to model enzymatic systems inside cells. So compartments would equal, the vesicle, the interstitial fluid, the outside the cell. So you could have multiple compartments and a rate constant associated with that transfer between different steps. Down here in kinetic parameters, you can see it just defaults every value to 0.1, and it defaults all these to 1 molar. So to make this a catalytic system, I'm going to use my aryl halide. I'm going to set that to 0.1 molar, so something like 100 millimole. Intermediate 1 at the beginning of the reaction, I've got none of that. My catalyst, I'm going to set that to a low value, so let's say 1 mole %. Your metal halide, let's do a slight excess of that. So I'm only starting with my aryl halide and my metal, 0.1 and 0.11. I have none of the salt, because that's a product, none of this intermediate, and no product when we start off. So I'm starting off with this is my general 0.1 molar in substrate, 0.11 molar in my excess reagent, and 1 mole % palladium 0. What I'm going to do down here is I'm going to set up these kind of generally. Again, you could start it here. This will kind of work. But I want to set this up where there's this little bit of forward bias. If I wanted this first step, this is the oxidative addition step. That's this step right here. If I want it to be product facing, I'm going to set this to some large value and the reverse reaction to some smaller value. So I want this to be equal to 1, and I want this to, why is that 1? I said B1, 1.0. You suck, man. B1. No. Okay. Sure. I don't know why it's doing that. Give me a second. Let me finish populating the rest ones. I want this to be 0.01, and I want this one to be 0.05. There we go. Oh. Yes, 1. No, oh my God. Sure. I don't know why he's doing that today. Forward-facing equilibrium still works. So, numerically, if you look at these two values, this value, the forward equilibrium constant for this reaction, is much larger than this one. So if I did this, the capital K value would be the ratio of these two. So 0.1, 0.001, I'm saying that this is a product-facing equilibrium. The second step, transmetallation, is an order of magnitude smaller than the smallest value up here. What I'm really saying there is, yes, this is small relative to that, but that is still smaller than anything else in this system. Setting this value very large, I'm just saying that this last step is very quick, right? Once I form this intermediate, it will break down quickly and do this reductive elimination quickly. This is the goal I'm trying to do, is set up the system so that the second step, transmetallation here, is my turnover limiting step for this system. All right, save that. Now I've got a catalytic system that has both initial concentrations the way I want and relative Ks the way I'd sort of expect for how the system's going to behave. I need to see something as an outcome. So I'm going to come down here to plots. I'm going to click a new plot. And if you double click into that, this gives you open this window. What we're going to do, and again, you can title it. I'm going to just call this one my time course. And I want a new curve that is going to graph, and you get to choose what do you want to put on X and Y. This is a useful thing because remember, right now we're trying to create a time course. That means along the x-axis will be the time associated with this reaction. The y-axis should be the concentrations of whatever I'm running. That's the normal thing you can imagine going into the reaction and doing. But there's a lot of other things you can do. You can actually graph individual species, their time components, their absolute rates. There's a lot of other variation on this, and we'll talk about some of these other more advanced things later. For right now, x, we want time. If you down-click, we've got two versions. Model initial time, that's not it. Model time is basically the running clock of the model if we evolve through time. So this is my x is model time. Y-axis, I want species, and I want transient concentrations. And I'm just going to, you can actually go through and pick one by one what you want to plot. I'm actually just going to highlight transient concentrations. So what that does is in one click, it will now do every concentration versus time pairing for whatever intermediates and whatever species you have. So this is where hygiene, I don't want any species up here that is not part of my system. If I went back through and I created a species like capital I intermediate, get rid of it before you start doing your plotting because you've got this hanging over value that's not associated with anything in your model. So you want to sanitize it, make sure that all these species are stuff that you're actually going to be using in the system. So now we've got individual concentration versus time for everything in the system, including the intermediates, including the free catalyst. Okay, now we got our plot. Now we're going to come up here to time course. And here I can take this value. If I click on time course here, what I'm saying is I want you to take the values I've specified up here, so the species, the reagents, and my parameter overview, everything I've specified here, I want you to run that model for 1 second, and I want 100 data points between time equals 0 to time equals 1 second. So I can just push run on that, and I get a very boring plot. When you push run, it will do the math. If you actually click down on time course here, it will now populate this result value, and you now have 100 points. We asked for 100 values, seen here. It's going to calculate some initial concentration. If you look across this, there's my initial palladium, my initial aryl X, there's my initial MR, everything else is 0. What it's doing is doing the math between, okay, you told me the K values were blah, you told me my initial concentrations, and you told me this is my pathway. It will take a small step recalculating those new values, so just dx dt for every linear equation, and then takes that initial value and does the next step and the next step. So all it's doing is an iteration of 100 individual calculations of whatever the concentration should be, evolving this model in steps. And unfortunately, what is this plot telling you? So if you look across this, what it's showing you up here, I'm going to go through these values you have up here. These are the things that you can plot. If I just hide everything, that is my aryl X against time. You can see I start at 0.1 and it drops to 0.099985. Barely did anything, right? If I plot the MR versus time, there's my 0.11, there's my 0.1. What's happening as you're adding and subtracting this is it's rescaling the y-axis to show you the best version of it. So close thing to do, and this is something that you train yourself into, look at my y-axis. The values having here is not from 0 to value. It's actually focusing in on 0.1 and 0.11, and they look like straight lines. What is this telling you? Yeah, you ran it for 1 second. What do you want? My gosh. This is a single second of a reaction right after it started. This is initial rate. I could look at this and say, well, there's the initial consumption of aryl halide. It's low. If I do this is my initial consumption of my MRX. It barely did anything because you need your intermediate to do something on that. What's also interesting is I can look at what did palladium do, and you can see it's tanking. It's going down quite quickly. My product versus time is just starting to come in, but it's like times 10 to the minus 10. So right now what we have is only a single, if I show all, that's every species in this thing, including my intermediates, including my free catalyst. Nothing much happened, right? Okay, so what I can do, close this window, back to time course. I'm going to give it more time. Let's give it 1,000 seconds. When I do this, usually when you manipulate this value, it will not change your intervals. So now it'll still do 100 steps, this time 1,000 seconds. If I push run now, still nothing, right? 1,000 seconds isn't enough. Okay, close it, add some more zeros, run it. Okay, now we're getting somewhere. All right, and we add some more zeros, run that. There you go. Now we have what looks like a normal time course curve, right? So let me blow this up. Now we've got something interesting we can look at. Now we've got sort of what looks like that's my normal curve of like product formation. Starting material goes away, and you notice, look at the gap between these two. Is it constant? Because what's the difference in mass balance here? Like we start off with a 0.1 and a 0.11. Why does it start to get wider at some point? Where's the rest of that mass between the starting materials going? Yeah, so think of it this way. Which value do you think is lower than it should be? You've got your red, your aryl halide, and you've got your other metal. We said, based on these equilibrium constants, which intermediate do you expect to build up? Based on how we defined a turnover limiting step, where's the turnover limiting step based on the values we did? First step, second step, or third step? Second step. If second step is a slow step, which intermediate is building up? This one. So I should see all of this is now over here. There's barely any of that. This should be your buildup, right? Okay, so we hide all. Let's look at just the intermediates. So palladium versus time. Oops, that's product versus time. Oh, no, that's palladium versus time. Palladium versus time actually shoots down to almost zero and then slowly returns. If we look at intermediate 1 versus time, it shoots up and is slowly being consumed. And intermediate 2 versus time is barely there. If I actually put them both on the same scale, intermediate 1 versus intermediate 2 is down here in the baseline. It never ever builds up substantially. But based on these values, that's kind of makes sense, right? It builds up. It's the predominant one where the free catalyst here is still sort of competing with it. So first off, visually, is this steady state? Not really.
Could you argue that intermediate 2 is at a steady state?
This is where it's a bit arbitrary. Is that steady state?
No, but it's so small the whole time that it's essentially...
And this is, yeah, absolutely. In the end, everything we're doing is some version of like mathematical assumptions. We're going to be basically building into this and making a bunch of different points. What I want you guys to do is I want you to be able to build up this, get as far as this point, be able to manipulate this. What I want you to try after you've done this is go into your parameter overview, play with these values, see how that impacts your concentrations of your intermediates. You should be able to get to something that looks more classically steady state versus what we see here. What this one's actually showing you, if you actually look into your plot, it's never really obeying steady state kinetics. Yes, it snaps over and intermediate 1 is kind of dominated initially, but then there's a trade-off where free palladium is actually the one that's winning over time. So homework is, for next one, get as far as this. Make sure you've got a version of this. Start messing with this and see what do you have to do to these values to actually get to something that looks more like a classic steady state system. All right, I will see you guys on Wednesday.